Hey, college algebra students, thanks for persevering through this midterm review. If you're getting a little weary, let me give you a couple of tips about the midterm. If you feel comfortable working these problems, you can work them confidently on your own and get the correct answer, then you're going to be ready for the test. The test will be set up very similarly to these problems. However, the test will be shorter than the midterm review. So rest assured, investing some time in this midterm review will really pay off on that exam. Let's work on dealing with even and odd functions in this section of the review. Number 27, determine if the following functions are even, odd, or neither. To determine if a function is even or odd, we're always going to start with the same test. We're going to replace all the x's in the function with negative x's. So everywhere I see an x, I'm going to replace it with negative x. So the first term becomes the quantity negative x cubed. Replacing the x in the red box with the negative x here gives me minus 2 times negative x and plus 1. Our next step is to simplify. On the first term, notice we are raising a negative number to an odd power. That always turns out to be a negative number. So we can drop the parentheses there, call that negative x cubed. On the second term, we have a negative times a negative, which is a positive, and we drop down our plus 1. Once I've plugged in negative x, I'm going to compare it to the original function. The original function is f of x equals x cubed minus 2x plus 1. I can tell that what I have obtained is different. Okay? If after I simplify, I get exactly the same expression as the original function, our conclusion would be that it is even. Now, comparing, notice the first term has changed sign from f of x to f of negative x. The second term has changed sign. Now here's the deal. If all terms change sign, it's going to be an odd function. Okay, let me state that again. If after simplifying all the terms are the same, it is even. If all terms change sign, it is odd. But you see how plus 1 ruins the party? That one did not change. So that we would say this function is neither even nor odd. Now looking at the exponents on this function, your intuition may have said this is going to be an odd function, but clearly it turned out to be neither. So make sure that you do run this test. All right, to write it abstractly here, if you simplify f of negative x and you get exactly the same function that you began with, your conclusion is it is even. If you simplify f of negative x and every term changes sign, the conclusion is odd. Let's work the next example to practice this concept. To determine if it's even or odd, I'm always going to start with f of negative x. So I'm going to replace all the x's in the original function with negative x's. Watch that double negative there on the middle term. We've got a minus from the function and a minus from the argument that we're plugging in. Okay, make sure we account for all the details here. On the first term, we have a negative number raised to an even power. That always turns out to be positive. So we have 3x to the 4th power. On the second term, when I evaluate a negative to an even, this gives me a positive number, but because of this additional negative, we're going to end up with a minus x squared there, and then plus 5. Once I'm done simplifying, I compare it to the original function. Notice the first term stayed the same, the second term stayed the same, and the last term stayed the same. So we have the case where we simplified f of negative x. We got exactly the same function we began with, so this one is an even function. Now, a shortcut for doing this, or maybe a visual approach, is to consider symmetry. Okay, so on problem number 29, I don't have a function where I can evaluate f of negative x. I have to make my conclusion based on the graph. So remember that even functions are symmetric about the y-axis. Okay, that means you could fold the graph in half on that y-axis, and you'd have two matching pieces on either side. An odd function, not symmetric about the x-axis, if that's what you were thinking. It's a little different. It's symmetric about the origin. Now, this is easy to remember. Odd functions are symmetric about the origin. Let me give you a picture of an odd function. A function that's symmetric about the origin has a radial or a rotational type symmetry. All right? So if I think about anchoring this graph at the origin, and I take this piece on the right and I rotate it around 180 degrees, notice that this piece would fit nicely right on top of this piece. That's what we call origin symmetry. If the function doesn't exhibit either of those behaviors, we say it's neither even nor odd. So the graph that we're examining here, notice I cannot fold it in half on the y-axis and get two matching pieces or two mirror images. So we know it's not going to be even. However, if I think about anchoring it at the origin and imagining if I could take this piece right here and pick it up and rotate it around, it's going to land on this piece right here. So we definitely are dealing with an odd function. Okay, you can go back to the other two right here and check those with your calculator. Let me demonstrate number 28. If we go to y equals on our calculator and we type in our function, which is 3x raised to the fourth power minus x, and do my shortcut square there. You can also do caret 2, and then plus 5. And I look at this in the standard viewing window, which, by the way, if you'll press zoom number 6, we'll all be looking at the same viewing window. Notice I have what looks like a parabola, but it's definitely symmetric about the y-axis. So I can imagine my y-axis here. I can think about folding this graph in half. I notice the right side is the mirror image of the left side. So it is an even function as we had determined. If we check number 27, when we graph that, we would see that it has neither type of symmetry, so our conclusion would be correct. Let's work on a couple of problems dealing with transformations, and we'll wrap up this video. We want to graph the function using transformations. When we graph by transformation, we have to identify the parent function. That is the most basic function or pattern that I can recognize from that given function. So our parent function, in this case, is the simple parabola y equals x squared, or you can call it f of x equals x squared. The graph of the given function will be related to x squared. So what I'm going to do is plot several points for this parent function, and then I'm going to apply transformations. So I'm going to pick out some really easy x values to use. -2, -1. These are just random numbers, and I'm choosing small numbers so it will fit nicely on our graph. If I plug each of these values into x and calculate y, if x is -2, y would be -2 squared, or 4. If x is -1, y would be 1. If x is 0, y is 0. And we continue evaluating. Then I have a set of ordered pairs that I can plot. So when x is negative 2, y is 4. So I'm going to plot the point negative 2, 4 on the graph. The next point is negative 1, 1. Then we have 0, 0, 1, 1, and 2, 4. Now you can certainly use colored pencils or highlighters to distinguish your curves, but if you're just using a pencil, you may want to consider graphing this as a dashed line. That's not my final graph, that's just my parent function. So I'm going to go ahead and label that one y equals x squared. Now, how does this relate to the function in question? Well, the function in question has several transformations applied. So notice I've got this negative outside the function. This means I need to reflect the original graph of our parent function across the x-axis. Okay, so I'm going to find a mirror image of each of those blue points that I graphed. I'm going to reflect them across the x-axis so our parabola opens down. So our first point was negative 2, 4. If I reflect it across the x-axis, find its mirror image, it's going to land at negative 2, negative 4. The next point at negative 1, 1 reflects below the x-axis to the point negative 1, negative 1. Our vertex doesn't go anywhere. It's going to stay right there. Reflecting the point 1, 1 across the x-axis, we end up at 1, negative 1. And finally, the point 2, 4 lands at 2, negative 4. So I'm going to dash this one in, not my final graph, just an intermediate step. If I wanted to label this with an equation, we just graphed negative x squared. Let's knock out the next two transformations in one step. Notice inside parentheses here, under the square, I'm subtracting 1. Now, if you've done your homework, you'll recognize this is a transformation to the right by 1 unit. So I'm going to move all of the points of that red graph where I ended up right by 1 unit. The plus 4, which is outside the function, is going to translate every point up by 4 units. Okay, so if it's inside the function, it's going to go the opposite way of what your brain wants it to. The negative 1 is going to move it to the right. And if the constant is outside the function, that means away from the square or the radical or whatever you're dealing with, it's going to go up. So I'm going to take each of those red points, move them right 1 and up 4. So starting with this bottom left point, I'm going to go right 1, up 4. That's its new location. The next red point on the graph, we're going to go right 1, up 4, and plot the point. Moving our vertex, our red vertex, right 1 and up 4. We'll land here. Next point, right 1 and up 4. And the last point on our red graph, right 1, up 4. We end up like so. Notice all these parabolas are the same shape and size. They've just moved to a different location relative to our parent function. So this is my final graph. I'm going to go ahead and label it. You can use f of x if you want to. I just happen to write a y. Same idea. Okay. Don't forget you can check this with your calculator. If you'll go back to your y equals, type in our new function. Make sure you use the negative, not the minus here. Negative parentheses x minus 1, close parentheses, squared, plus 4, and hit graph. You'll see the final function that we determined. If you want to check those point by point, here's a great function to know. Above that graph button, you have table written there in blue. So if you'll do your second key and then your graph button, you'll be able to try that again. Second table, you can see this is the location of all the points where we ended up. So it's a great thing to know how to check your graphs. Next question, use complete sentences to describe the process of graphing f of x equals 2 square root of x plus 1 minus 4 using transformations. It's a similar process to what we were just examining on problem 30. We just have to describe our steps as opposed to actually graphing them. So the first thing we do is identify the parent function. So the first thing we want to do is graph the parent function, which in this case would be the simplest square root function that we can think of. Notice we don't have a negative out front, but we do have this multiplier 2. That's a stretch. Okay, remember, if it's bigger than 1, it's a stretch. If it's less than 1, it's a shrink. So we can say stretch the graph by a factor of 2. And then remember, when you have a constant inside the function, that's under a square root, inside absolute value bar, something like that, then the sign is going to indicate the opposite direction. So a plus 1 inside the function means that the graph should move to the right by 1, to the left by 1, and the minus 4 out here means we should move the graph down 4. So move the graph left 1 and down 4. And that's that. You'd have a graph done by transformation. All right, in the next video, we'll talk about operations on functions.